In this video we're going to take a look at the booklet on the reactions of halogenoalkanes, focusing on nucleophilic substitution mechanisms, the rates of hydrolysis and elimination reactions. So why do we use halogenoalkanes at all? Halogenoalkanes are very useful compounds, particularly in organic synthesis. They are more reactive than alkanes, and so they can be used as precursors, so that means starting compounds for the synthesis of more complex molecules. In their own right, they're useful as refrigerants and solvents, but that can be problematic because, as we've also studied, chlorofluorocarbons, which are a type of halogenoalkane, are damaging to the atmosphere, in particular on the ozone layer. This particular booklet is going to focus on organic mechanisms for halogenoalkanes, and I'm going to run reasonably swiftly through them and get onto the worked examples. So the first type of mechanism that we're going to look at is called the nucleophilic substitution reaction. Because halogenoalkanes have got a delta positive carbon atom, here we go, I'm going to circle it for you there, it's going to attract the lone pair of a nucleophile. A nucleophile is a substance with a lone pair, may also have a negative charge, but definitely has to have a lone pair. And in this case, the nucleophile is the Cn- ion. So this is our nucleophile. So in this mechanism, the nucleophile attacks the delta positive carbon. That then involves the removal of a Cl- ion, a chloride ion, and the replacement of the chlorine atom in the molecule with a Cn nitrile. So the consequences of that in this particular case is to go from chloroethane to propane nitrile. Conditions for this reaction are the required halogenoalkane and potassium cyanide, which is a salt dissolved in aqueous ethanolic solution. The little bit of ethanol helps for the organic substance, the halogenoalkane, to dissolve into solution with the salt, potassium cyanide, which is soluble in water. The consequences, the product of this is called a nitrile. So that's something containing the C triple bond N functional group. So that's a nitrile functional group. And the naming convention for nitriles is to give the chain first. So in this case, it's now a chain length of 3, 1, 2, 3. So propane, and then ending in nitrile. Because the chain has lengthened through this process, so we started off with chloroethane and we've ended up with propane nitrile, this is a useful reaction for chain lengthening. A very similar reaction can occur between the delta positive carbon of the chloroethane, and in this case we've got the hydroxide ion acting as our nucleophile. As previously, it has to have a lone pair and it carries a negative charge, which it doesn't have to have, but that helps with the attraction towards the delta positive carbon atom. So there are two possible reactions with sodium hydroxide. One possible reaction, if we use warm aqueous solution, is to do nucleophilic substitution, and we'll find out a little bit more about the alternative reaction later on. The reagents and conditions then are warm aqueous sodium hydroxide and reflux. The product in this case is an alcohol of the same chain length as the starting material. Although we're making an alcohol, and in this case with chloroethane as the starting material, that alcohol was ethanol, we wouldn't usually use this reaction ethanol in any great quantities, because actually the halogenoalkane starting material is worth more than the ethanol that can be obtained much more cheaply via reactions such as fermentation reactions. However, in molecules other than ethanol, this nucleophilic substitution reaction can be used to carefully put an OH group into the right location on a molecule for the purposes of the synthesis that you're trying to achieve. When you do the same reaction, nucleophilic substitution, but with ammonia acting as a nucleophile, which it can do because it has a lone pair, you'll notice that because it is a neutral molecule, there is an extra step here where ammonia acts as a nucleophile in the same way as before in the first step, attacking the delta positive carbon atom and removing the chloride. But that will then give us a positively charged intermediate. So if we're thinking about where the marks can be sought here, we'd get the first marking point M1 for the first arrow, the second marking point M2 for the second arrow, the third marking point M3 is for the structure of the intermediate. So it's really important for this third mark that the nitrogen is making 4 bonds, 3 to hydrogens, and that it's shown with a positive charge, otherwise you won't get M3. M4 is usually this arrow here. Usually this bit up here is shown in brackets, meaning that it's correct, but it doesn't gain a mark. Okay. The second step here is ammonia acting as a base to deprotonate that amine to give you the final amine product. The reagents and conditions here are excess concentrated ammonia. The reason that we use an excess of ammonia is because the amine that has been formed is also capable of acting as a nucleophile. Okay, so I'm going to show you a little supplementary mechanism down here now, which is quite interesting. So we've got some of our starting material, chloroethane, and what's possible to happen is that the amine, which has been formed from the first reaction, is capable of acting as a nucleophile, and it can attack this delta positive carbon. Looks quite interesting, doesn't it? And this delta positive carbon then is going to end up, show you what this looks like. So we're going to end up with our nitrogen. Our intermediate step is going to be making 4 bonds. So that's our intermediate step, plus Cl minus, and then another molecule of ammonia from the starting material can attack that, and that's going to make our final molecule here. And then hopefully you can see that, quite interestingly, this molecule also has a lone pair. So this is now a secondary amine. So this is a primary amine because the nitrogen is bonded to 1 carbon atom. In the example below here, I'm just going to change pen colour so you can see, my nitrogen is bonded to 2 carbon atoms, so it's secondary. Well, in actual fact, that molecule can also act as a nucleophile, and the product of that, I'm just going to draw the product of that up here. And now this is a nitrogen atom which is bonded to 3 carbon atoms, And so this is called a tertiary amine. Now the quick-witted amongst you might have noticed that this tertiary amine also has a lone pair, so it can act as a nucleophile. And so finally we can make one more substitution, and this makes this thing here a quaternary ammonium salt. This is now carrying a positive charge. There is no lone pair. It's called quaternary because it's a nitrogen making 4 bonds to carbon atoms. So that ion then becomes associated with the Cl-. And in this point in the synthesis, we actually produce a crystalline substance. So in year 12, we just need to know the mechanism to just make a primary amine. But you do need to be aware that further substitution, because each of the products remains a nucleophile because it has a lone pair, we can go all the way to a quaternary ammonium salt where 4 substitutions have taken place. And we've gone through primary, secondary, which is this one here, tertiary amine, and then finally to quaternary ammonium salt. Fun fact, these quaternary ammonium salts are what makes shampoo have that sort of, some might call it silky, but silky sort of slimy feel to it. So quaternary ammonium salts are found in hair conditioners. So let's take a look at some of the exam style questions. Okay, the first one, the question below refers to the reaction of 1 bromopropane with a solution of potassium cyanide in aqueous ethanol. What is the organic product of this reaction? So we've got 1 bromopropane. It's going to do a substitution reaction. Here's the bromopropane. We're going to end up with this one. That's 1, 2, 3 carbon atoms. So it's going to be propane, and then the functional group is the nitrile, so propane and nitrile. Let's have a look. Oh, hang on a minute. I do apologise, I've misread the question. We're starting with 1 bromopropane, and I've drawn bromoethane, so let's try again. It's 1, 2, 3, 4. So our substituted product has now got 4 carbon atoms, so it's actually butane nitrile. So bromopropane is going to extend its chain length with cyanide, so it's going to become 1 plus 1 carbon atom bigger on the chain. Let's have a look at exam question 2. This question is about a method that can be used to produce methyl amine. So we've got the halogenoalkane, bromoethane, and 2 molecules of ammonia. So in the first one, the ammonia atom attacks the delta positive carbon, which is as we'd expect. So I'm happy with the 2 arrows, one coming in here and this one. The question is asking which one is incorrect, so within 1 I think that's fine. In 3 we've got the ammonia acting as a base, always start at the lone pair, going to this hydrogen, I'm fine with that. But the electrons have to continue further into the molecule, so this one is pointing in the wrong direction. Remember, we can never have a situation where two arrows come together like this in a mechanism under most circumstances. We want to be following, the arrows are going to go through the mechanism more or less like this, between lone pair to bond, lone pair to bond, bond onto atom, etc. So the incorrect curly arrow is arrow number 4. That's answer D. Pentane nitrile can be made by reaction of 1-bromobutane with potassium cyanide. So we've got 4 carbon atoms here. This potassium cyanide, Cn-, is going to do a nucleophilic substitution to add that additional carbon. So let's have a look, what's the correct name? We've got electrophilic ones, and then we've got 2 possible nucleophilic ones. Nucleophilic addition, no, we do that one in year 13 though. Nucleophilic substitution is correct, because the product, so we've got the product, ooh, we'll do a zigzag, it's turned it into a straight line. It doesn't like carbon backbones. 1, 2, 3, 4, and 5 is propane nitrile. 1, 2, 3, 4 is bromobutane. Exam question 4. 3 different ways of producing ethanol are shown above. So in reaction 1, I'm just going to annotate it a bit for you here. We've got glucose to ethanol. Glucose, which is a form of sugar, to ethanol is our fermentation reaction. Reaction 2, bromoethane to ethanol. So that's the one we've just been talking about. That's our nucleophilic sub with OH- in warm aqueous. And reaction 3 is the steam hydration of ethene, something that we study in a bit more detail when we look at the reactions of alkenes and alcohols very shortly. Reaction 2, so this is our nucleophilic substitution, give reagents and conditions. So we've got the reagent for the hydroxide nucleophile is sodium hydroxide in warm aqueous solution, and we're going to reflux. So reflux is where we are heating and simultaneously condensing using a vertical Liebig condenser. So we heat the mixture so that the reaction can take place. Vapours, however, are formed. They travel up into the condenser where they can be condensed. As they travel higher, they get cooler, they condense, and they run back down. So the reaction can continue over an extended period of time with evaporation and condensation and re-dropping back into the flask. Mechanism for reaction 2, we've got bromoethane, we've got the nucleophile is the hydroxide ion, delta positive carbon, delta negative bromine. That's the mechanism, and so our product is the ethanol. We might notice that I do tend to draw mechanisms in skeletal formula. I do find it's considerably easier like that, but I just want you to be aware that it is also valid to draw a mechanism if you prefer. You can draw a mechanism as a displayed formula, and sometimes some students do really prefer that, and that's also okay. The only thing I would say is if you are doing either of these mechanisms either with skeletal formula or displayed formula. Just work carefully to make sure you don't miss any hydrogens off in the case of the displayed formula, and in the zigzags always just go back through and count the number of carbon atoms. It's easy to sometimes make a mistake on the zigzags. Select a reason other than safety why this method is not used in industry to synthesise ethanol. So we've already mentioned this so far, but basically this is a very expensive process because bromoethane is an expensive starting material. Note how I haven't just said it's expensive. The other thing which we know by the time we get to the end of the booklet, and we've covered this in lessons, is the fact that there is an alternative product that can form with hydroxide, and we could have elimination also occurs, and that will happen to some extent even in warm aqueous sodium hydroxide. So there are there's more than one potential product. The mechanism with ammonia is the mechanism which is a bit more complicated, and that's because it's a neutral nucleophile, and so it goes via a two-step process, starting as always with the lone pair on the nucleophile, which is attracted to the delta positive carbon, breaking that bond. But this time we get some additional marks for the intermediate, which has a positive charge on the ammonia, on the ammonium ion, and then the ammonia which is present in the solution can also act as a base, can remove a proton, and that gives us our final product, the amine, which is as given in the question here. Remember, when we get to year 13, we've got to think about the fact that that could do further substitution. It's not going to be part of the question at year 12 level. We've outlined the mechanism. Let's make sure we've named it as well, because that's in the question. So this is a nucleophilic substitution reaction. We've got to be able to name the mechanisms that have taken place. Nucleophilic, because it involves the nucleophile, NH3, and substitution, because the bromine that was on the original compound has been replaced by the amine group. Okay, so with this question we've got to give several definitions. So this is a good example of where learning your definitions is a route to some relatively straightforward marks, assuming you've learned them. Okay, so first of all, a nucleophile. So basically it is the lone pair is doing all the work here for a nucleophile, so it's an electron pair donor. Okay, could also say a lone pair donor. It's important that it's a pair, it's not just an electron donor. If we look back at this mechanism, here is the electron pair, very important. Substitution, okay? Substitution is exactly what it says on the tin here. It's where we replace, so replacement of the halogen in a halogenoalkane or haloalkane, same type of compound. So this is in particular as applied to the halogenoalkanes, replacement of the halogen in a halogenoalkane with the nucleophile. Okay. Hydrolysis. So I love this one. Okay, we split that word into two. Hydro is water, lysis is split. So we've basically got splitting a molecule using water. So that's hydrolysis. And bond enthalpy. So the bond enthalpy is because it's enthalpy, so it's the heat energy required to break a carbon halogen bond at constant pressure. Outline a mechanism for the nucleophilic substitution reaction in which 2-bromopropane. Oh, I've added it in the wrong place. Just putting it on the end. React with potassium hydroxide to form propan-2-ol. So here's our 2-bromo. I've done bromobutane. So what I mean about just adding up your bonds, it's easy done. 2-bromopropane, and our hydroxide is going to come in here. And that's going to produce our propan-2-ol. 2 marks for that, obviously. And 1 and 2. So you might ask the question, okay, and it would be a reasonable question to ask, how do we know that that's actually what happens? Well, we can use kinetics, and it is possible for us to investigate these reactions by working out how varying the concentration of the different reactants affect the rate of the reaction. From that we can calculate something called the order of the reaction, and that tells us a little bit more about how many molecules are involved in the rate determining step, so that's the slowest step in a reaction. That's really useful, and I do have a section in an extension sheet going beyond A level which introduces you to these first and second order mechanisms. There's a little bit about the alternative that you can see here. So in this alternative we can have a mechanism where in the first step the first step is the breaking of the CBr bond in this case. Now that's not likely to happen if we've got a primary carbocation. So a carbocation is a positively charged carbon. So if this was, let me draw you an example. This would be an example of a carbocation that would be very unlikely to form. So it would be very unlikely to make this carbocation because it's a carbon atom bonded to no other carbon atoms whatsoever. So there's not much stabilisation there. This is a carbon atom bonded to one other carbon atom. So that's a primary carbocation which has a slightly more stability. A secondary carbocation which is a carbon bonded to two other carbon atoms, and finally a tertiary carbocation, so a carbon bonded to three other carbon atoms. So we've got, in terms of stability of these cations, we've got this one at this end is the most stable, and at this end is the least stable. So the mechanism that we've been learning at the moment, the nucleophilic substitution mechanism, which shows the nucleophile coming in and simultaneously the leaving group, the bromine, chlorine or iodine, leaving as iodide, bromide and chloride respectively. That's happening in most of the cases where it's less stable, so towards the left hand side. The more stable it gets, so the more tertiary carbocation here, so this is more stable intermediate, the more likely the mechanism is to proceed via this different mechanism that we haven't learned about. Okay, so these are unimolecular methods and bimolecular methods where there's a second step of a molecule doing a second step. Least stable, most stable. So we did a practical activity 24, which compared the rates of hydrolysis of halogenoalkanes. So if you have a look at practical activity 24, you'll see that you're given a table of information that shows that the bond polarity increases in that direction, with the fluorine having the most polar bond and the iodine Ci having the least polar bond. And this way got a decreasing bond enthalpy. So let's have a look at some of the questions regarding this practical. So in this practical you put together in some test tubes some silver nitrate solution and some of the halogenoalkane in an aqueous solution with a little bit of ethanol to help the two to mix together. Then you observed how quickly a precipitate was formed. The precipitate that would form if the CCl bond was broken would be the silver chloride, which is a white precipitate. If it was with the halogenoalkane that's bromine, you would get a cream precipitate, a silver bromide, and with the iodine halogenoalkane you would form the silver iodide, which is yellow, so with the iodo compound. The reason that we don't see a precipitate formed is because silver fluoride is aqueous. It's not a precipitate, it's soluble in water. So, suggest the order of reactivity if the polarity were the only factor. So if we have a look at the trend there, the most polar bond is CF. So the trend would suggest CF, CCl, CBr and CI. So the rate would decrease as you go towards the CI, and the rate would be at its fastest at CF and CCl. Now obviously in our experiment we're just going to start at CCl because the CF is going to form an aqueous silver fluoride. So, suggest the order of reactivity for the halogens if the bond enthalpy were the only factor. Okay, so if the bond enthalpy were the only factor, Ci has the weakest bond, and so would react most quickly. So we'd have Ci, CBr, CCl. Again, we'd have here the fastest, going to the rate decreasing. And so the one that actually matches up most closely to what we physically observe when we do this experiment is number 2, that the Ci is the fastest, so produce that yellow precipitate of silver iodide the fastest. So the factor that's most important is the bond enthalpy is the most important because the Ci bond hydrolyzes the fastest. Why must excess sodium hydroxide be neutralised before adding silver nitrate? So if we were to use, instead of using water and doing hydrolysis, if we were to split the molecule using sodium hydroxide, that would happen, from a nucleophilic substitution point of view, that could happen, but there's a bit of a problem. And the reason for that is that silver ions form another precipitate, silver hydroxide, and that precipitate would prevent us from seeing the formation of the desired precipitates, the silver iodide, the silver bromide and the silver chloride. So silver hydroxide would form, masking the presence of the silver iodide, silver bromide and silver chloride. Just for your information, the silver hydroxide is a white precipitate, the perfect thing to hide the presence of the other precipitates. Explain why using the same number of drops of each halogenoalkane is not a fair test, and suggest how this could be achieved. Well, the halogenoalkanes all have different densities. So a similar volume will have a different mass and different number of moles. So we must have to use the same mass as opposed to the same volume, or calculate equivalent volumes from the density. So basically a drop with the same volume, but it would be a different mass because the densities of these substances would be different, and therefore the size of one drop contains a different number of moles for each of the examples. So let's have a look at some of the exam questions together. So exam question 7, the question is asking, in relation to this reaction, 1 bromopropane with solution of potassium cyanide in aqueous ethanol. The reactions of 1 bromopropane and 1 chloropropane with potassium cyanide in aqueous ethanol occurs at different rates under the same conditions. Which row correctly shows the compound that has a faster rate of reaction and the correct reason for this? So let's have a look. The ones that occur faster are going to be the bromo compounds, so I could have to rule out C and D. And let's look to see which one has the correct answer. In part A, it's that 1-bromopropane has a weaker CBr bond than a CCl bond, and in B, it's the other way around, but the correct answer is A. The weaker bond, the weaker bond breaks more quickly. The rate is increased, and the 1-bromopropane has a higher rate of hydrolysis than the chloropropane. So that's A. A student carried out an experiment to study the rates of hydrolysis of some halogenoalkanes. In the experiment, 2 different haloalkanes were placed in separate test tubes containing silver nitrate. The haloalkanes reacted with the water in silver nitrate, and the student timed how long it took for the formation of the precipitate. Okay, so we've got a little table. What is the meaning of hydrolysis? So splitting the CX bond, crucially using water. Splitting using water is what hydrolysis stands for. State the colour of the precipitate formed when iodide ions react with silver nitrate, and the simplest ionic equation. So a bit of a kickback from GCSE now. Iodides react to form yellow precipitates, and we've got aqueous silver ions reacting with aqueous iodide ions to form a precipitate of silver iodide. You can use that for all of them. Obviously the colour of the precipitate is different, cream in the case of the bromide and white in the case of the chloride. Remember though that we can't do this with the fluoride because silver fluoride is soluble in water. So just as a bit of an aside, just down here, the silver ions plus fluoride ions goes to silver fluoride that's also aqueous. There's no precipitate. Use your knowledge of the reactions of halide ions with silver nitrate to suggest why the student did not include 1-fluorobutane. I should have preempted that. So AgF is soluble in water and does not form a precipitate. Okay, so you wouldn't see a difference. Can't do an experiment where we can't time a change like this. We can do experiments where we don't always time something, but in this particular instance, if we don't see anything happening, this reaction, we're not going to get any information unless we come up with a different method of detecting that. The student used the following enthalpy data to try to account for the different initial rates of hydrolysis of the halogenoalkanes. The student deduced that the rate of hydrolysis is influenced by the strength of the carbon-halogen bond. Suggest how the experimental evidence enabled the student to make this deduction. Okay, so when we're looking at this, we want to link together the bond strength with the speed Okay, so the weaker the bond enthalpy, so that would be a lower value, would make it weaker. So 238 is lower than 276. So the weaker the bond enthalpy, so the lower the value, the higher the rate of reaction would be expected to proceed. So the weaker the bond enthalpy, the higher the rate of reaction would be expected to proceed, and the less time it would take for a precipitate to appear. I think I've written a lot for 1 mark there, but that just about sums it up. So the weaker the bond enthalpy, so that's a lower value, the higher the rate of reaction would be, and the less time it would take for the precipitate to appear. Okay, the nucleophile then. So a nucleophile is either a lone pair donor or an electron pair donor. When a hydroxide ion collides with a molecule of 1-bromobutane, the following reaction occurs. Outline the nucleophilic substitution mechanism. So we've got 1, 2, 3, 4 bromobutane. There we go. And that's delta negative, this is delta positive, and the OH minus is going to do this. Oh, it's done that funny thing again where it doesn't like my zigzag. Okay, so we're going to have M1 for the first arrow, M2 for the second. The reaction of hydroxide ions with 2-bromo-2-methylpropane may occur by a different mechanism. So this is where I've mentioned we're not necessarily on the A-level syllabus. So this is like a question which has extended the students answering this question for the first time to think about a different mechanism. There is only one mechanism on your A-level syllabus, so this different mechanism is a bit of a curveball on this particular exam question. This different mechanism involves the formation of a carbocation. So carbocation is a positively charged carbon atom. So logic is what's going to get us the first answer. Complete the following equation by drawing the structure of the carbocation formed when the CBr bond is broken. So if a neutral molecule is broken to give a positively charged and a negatively charged species, we're just going to draw out what's left once the bromine has left. And that's this carbocation here. Why this reaction might occur by this mechanism is because tertiary carbocations are more stable than, so if we have a look at the reaction in part C2, okay, so in this one we've got a carbon atom which is just bonded to one other carbon atom, so the bromine is on the end, so that makes it a primary. Tertiary carbocations are more stable than primary carbocations, and that's why there is a tendency for this reaction to proceed via this different mechanism when there is a very stable carbocation, so in other words a tertiary carbocation intermediate. The second type of mechanism that we're covering with halogenoalkanes is called elimination. Elimination happens when, instead of acting as a nucleophile, the hydroxide acts as a base and removes a proton. That's illustrated in the mechanism that you can see here. And the difference, if we want elimination to take place, is that we want to prioritise the presence of hot concentrated sodium hydroxide or potassium hydroxide in ethanolic solution rather than water and reflux. In these ethanolic conditions, the hydroxide ions are more encouraged, they are more likely to act as a base, taking a proton, than they are as a nucleophile. There's far fewer protons available in a solution of the ethanolic solution, so it's easier for the hydroxide, it's more likely for it to act as a base. So let's look at the example. There are usually several places where the base could attack and remove a proton. So you can see in this first instance, we've got the base attacking this hydrogen here, which is shown as a red hydrogen. That then forms a double bond here before the bromide ion leaves, and that puts the double bond at the end of the molecule. In the case of the second option, okay, so we've got the hydroxide ion attacking this middle carbon atom. That is creating a double bond here, and again that's removing the bromide ion. Now in this second example, depending on the rotation of the original compound, the nucleophile, the attack of it can produce two stereoisomeric products. So they can be E pent 2E, and I'm just going to draw some mirror lines so that we can have a look at the E and the Z. So when we are assigning the priority on an organic compound like this, that's a hydrogen and that's a hydrogen. So we have to look at both sides of the dotted line and decide which species has the highest priority. So we've got the carbon has higher priority than hydrogen on the left hand side, and the carbon has priority over the hydrogen on the right. That makes this compound entgegen, or on the opposite sides, which is E. In the second example here, we've got, I'm just going to draw in the hydrogens. On the left hand side of the dotted line, we've got carbon with priority over the hydrogen, and on the right hand side we've got carbon with priority over the hydrogen. This means the two priority groups are on the same side, and this becomes Z, zusammen, the same side. So from one molecule, the halogenoalkane, there are two potential positions where a hydrogen could be attacked, the green positions and the red positions. Attack on a red position puts the double bond on the end. Now if we have a look at the double bond on the end, which you might be saying to yourself, well, why haven't I drawn an E and Z for that? Well, let's just fill in the missing atoms. Put the big up there to the hydrogen. And let's add a mirror line. On the left hand side of the mirror line, we've got a carbon, which takes priority over the hydrogen. On the right hand side of the mirror line though, we've got two of the same. So it's not possible to have E or Z when on one side of the double bond you've got two of the same thing, because I could just turn that molecule over and that would give me the solution. So if we attack at the end of the chain, we don't get a pair of stereoisomers. If on the other hand the attack forms a double bond in the middle of the chain, then we do get stereoisomerism and we get E and Z. So let's have a look at some of the questions relating to this. Which compound is not formed by reacting 3-bromo-3-methylhexane with warm ethanolic potassium hydroxide? So we're going to be making all of these are alkenes. So in all of these cases, we're going to be making just an elimination reaction. Let's have a look. We've got just a minute. And we've got our 3-bromo, 3-methyl, 1, 2, 3. Bromo and methyl. Okay, so this is the carbon atom that, I'm just going to put a little blue dot, that's the one that the bromine is attached to, so we can take hydrogens here or on the other side here. So if we just have a look at drawing the final product then, so we could either have our double bond here, or we could have doing that funny thing. That could be here. Okay. So that's the two potential locations. Which compound is not formed by reacting 3-bromo, 3-methylhexane with warm ethanolic potassium hydroxide? So we've got our two possible positions. Let's have a look at the answers. So we've got in terms of these two, let's see if we can find these amongst our compounds. We know these two versions are named. So we've got 1, 2, 3 methyl hex 2-ene. So that one is C. Then 3 methyl 1, 2, 3 methyl hex 3-ene is that one. So that's D. So we know that C is formed, and we know that D is formed. So do we have any other options? So let's have a think. We could actually have a hydrogen on here as well. And when that goes, that's going to make this compound okay, so that's going to go into here like that and off there like that. So that's going to make this one. So let's think about it. This is 1, 2, 3, 4, 5. So that's pent 1-ene with an ethyl group. So this one is A. So A, C and D all happen, and so the one that mustn't happen is B, which is 3-methyl hex 1-ene. That's quite tricky because I think you would struggle just with that last bit of those hydrogens on the methyl group, just reminding you that you can get compound A. When 2-bromopropane is heated with ethanolic potassium hydroxide, an elimination reaction occurs. State the role of the potassium hydroxide. So in this instance, the potassium hydroxide is acting as a base. The mechanism, so what have we got then? We've got 2-bromopropane. Oh, hang on a minute, I've done the same thing again as before. I've done 1-bromopropane, 2-bromopropane, and the OH minus is going to attack. It doesn't really matter in this instance which side it comes at, because this is actually symmetrical. So those are our 3 arrows. And so that solution to that is going to be this molecule here. This is going to be a different one because our hydroxide here is doing the nucleophilic substitution because the CBr has been replaced by a COH. So the mechanism here is nucleophilic substitution. Okay, so the mechanism then for our nucleophilic substitution, because I always tend to draw the skeletal formulas, dot positive, dot negative. So thinking about the marking points, we should be getting quite familiar with these now. M1, M2. So tick, tick, tick. Name the haloalkane in this reaction. So it's just drawn, isn't it? So the haloalkane, we've got 1, 2, 3 carbon atoms, and it's got a bromine on the second one. So our name for this reaction, for this molecule, is 2-bromopropane. Identify the characteristics of the haloalkane molecule that enable it to undergo this type of reaction. So this is one of those questions where you might think I haven't the faintest idea what that's asking, but actually we talk about it every single time, and it contains a delta positive carbon atom which attracts the nucleophile. Remember what I said earlier, you could use even better terminology. You could say a delta positive carbon atom, and another way to say that is to call it electron deficient. So the electron deficient carbon atom attracts the nucleophile. The other reaction that can occur with potassium hydroxide acting as a base, that's what we've got here, to form the alkene. The name of the mechanism here is called elimination. If you're wondering why that is, it's because it eliminates a molecule of water out of it. So effectively ejects a molecule, so that's called an elimination reaction. The mechanism, and this time we're going to need some hydrogens that are adjacent to that carbon. The hydroxide ion attacks and that's our product. Okay, so you can see we've got nucleophilic substitution taking place when we've got hydroxide to make an alcohol, and elimination taking place when we've got the concentrated ethanolic hydroxide. Give one condition needed to favour the reaction shown in part B. So to favour the elimination reaction, there are various things we can do. So we can dissolve it in ethanol, so ethanolic solvent. We have concentrated NaOH or KOH, hot, as opposed to warm. So ethanolic solvent, concentrated sodium or potassium hydroxide, and hot, and that will favour the elimination reaction. So please go back through, make sure that your own booklet is completed, and that you have used the videos to help you with any understanding, but obviously bring that to me if you're still having any difficulty.